In 1932, if you wanted 8 cylinders under your hood and you weren't rich, you were basically out of luck. V8s lived in expensive luxury cars or low-volume racing specials, far beyond what ordinary buyers could touch. Cadillac had been building V8 engines since 1914, but they were complex, expensive, and reserved for luxury buyers who could afford both the initial cost and the skilled maintenance these engines demanded. Other manufacturers had produced small numbers of V8s, but always as expensive, hand-built engines that required frequent adjustment and specialized maintenance. What working Americans needed, and what no one had figured out how to build, was a V8 engine cheap enough, durable enough, and simple enough for trucks, work vehicles, and everyday use. It wouldn't be the first V8, but it would be the one that put real power in the hands of ordinary people. In the heart of Ford Motor Company's engineering department, a team of engineers faced what many called an impossible task: build a V8 engine that was powerful, affordable, and could be mass-produced for everyday vehicles. At the center of it was Eugene Farkas, a brilliant Hungarian immigrant with a knack for solving the unsolvable. Henry Ford had made the call. Now it was up to Farcus and his team to engineer it into reality. Most engineers would have politely explained why it couldn't be done. Farcus rolled up his sleeves and got to work. Eugene Farkas arrived at Ford in 1913, like many European engineers of his generation, drawn to America's industrial boom. Born in Budapest in the late 1880s, he'd studied mechanical engineering at the Royal Hungarian Technical University before the chaos of World War I scattered his generation across the globe. Unlike many immigrants who started at the bottom, Farkas's technical expertise quickly caught attention at Ford's expanding Dearborn operations. By the mid-1920s, Farkas had become a key figure in Ford's engine design and casting development. While other engineers focused on theoretical performance, Farkas obsessed over practical manufacturing. He understood that the most brilliant design was worthless if it couldn't be built efficiently, reliably, and cheaply. Henry Ford had been fixated on V8 engines since the late 1920s, but his obsession went beyond mere mechanical fascination. He wanted to give working Americans access to real power, and blunt Chevrolet's rising six-cylinder threat in one bold move. The Model T had democratized transportation, but its simple four-cylinder engine was showing its age. The Model A's improved four-cylinder was better, but still limited. Ford wanted to leapfrog the competition entirely with an engine that would give working-class Americans access to genuine power. The problem was that every previous attempt at mass-producing affordable V8 engines had failed spectacularly. Chevrolet had tried in 1917 with a V8 that ran hot, proved troublesome, and was dropped after a short run. Cadillac's V8s were engineering marvels, but they cost more than most people made in a year and required skilled mechanics for proper maintenance. The fundamental challenge wasn't just engineering, it was manufacturing philosophy. Traditional V8 engines, including Cadillac's sophisticated designs, were assembled from multiple separate castings, bolted together with dozens of gaskets and seals. The cylinder blocks were cast separately, then machined and fitted to a separate crankcase. Timing covers, oil pans, and cylinder heads added more complexity. Each joint was a potential failure point, and the precision required for proper assembly made mass production at affordable prices nearly impossible. Ford's existing production methods were built around relatively simple engine castings that could be machined quickly and assembled with minimal skill. The Model T's four-cylinder engine used just 4 major castings, while a typical V8 required 16 or more separate pieces. Scaling up to V8 production would require completely new foundries, different machining equipment, and retraining thousands of workers. But Henry Ford wasn't interested in conventional wisdom. In 1930, as the Great Depression devastated the American economy, Ford made a decision that his own executives called financial madness. He committed tens of millions of dollars, hundreds of millions in today's money, into V8 development and tooling, putting the money on the line even before the design was finished, a gamble that could bankrupt the company if it failed. The project landed on Eugene Farkas's desk with a simple but daunting mandate: design a V8 engine that could be manufactured using Ford's existing production philosophy while delivering the power and reliability that American buyers demanded. Farkas became one of the central engineers in a small team that Ford tasked with making a mass-market V8 possible, working alongside production chief Charles Sorensen and the foundry team. He understood immediately that success would require abandoning everything the industry thought it knew about V8 design. His breakthrough came through a radical reimagining of V8 architecture. Instead of assembling multiple separate castings like Cadillac and other luxury manufacturers, Farcus proposed casting the entire engine block as a single piece, a monobloc design that would eliminate dozens of potential failure points while dramatically simplifying assembly. The approach was theoretically sound but practically unprecedented. No one had successfully mass-produced a complex 90-degree monobloc V8 at Ford's target volume and price. The technical challenges were staggering. Molten iron had to flow through complex internal passages while maintaining uniform wall thickness throughout the casting. Water jackets for cooling had to be integrated into the casting itself, with passages connecting all 8 cylinders. The crankcase had to be strong enough to handle the forces generated by 8 pistons, while remaining light enough for practical use. Farcus spent months developing the casting process, working closely with Ford's foundry specialists to perfect every detail. The sand molds had to be precisely formed with cores that created the internal water passages. Each block required hundreds of pounds of molten iron poured in a tightly controlled, continuous stream. Temperature and cooling rates had to be managed carefully so the metal filled the complex passages without cracks or internal flaws. The breakthrough came when Farcus realized that the key wasn't just in the casting process, it was in the engine's fundamental design. Instead of using overhead valves that required complex cylinder heads and valve trains like the luxury V8s of the era, he proposed a side valve design where both intake and exhaust valves were located in the engine block itself, operated directly by a centrally mounted camshaft. This flathead design earned its name from the completely flat top of the engine block. With no valves protruding into the combustion chambers, the cylinder heads were nothing more than simple iron plates that bolted directly to the block. The design sacrificed some breathing efficiency. The L-shaped combustion chambers weren't ideal for airflow, but it made the engine incredibly simple to manufacture and service. The valve arrangement was elegantly simple. Each cylinder had 2 valves positioned side by side in the block, with the camshaft located in the valley between the cylinder banks operating all 16 valves through simple mechanical lifters. No push rods, no rocker arms, and a simple gear-driven cam instead of elaborate timing hardware. The entire valve train used far fewer moving parts than a comparable overhead valve V8, which helped reliability and cut costs. But simplicity came with its own challenges. The side valve design created unusual combustion chamber shapes that could cause hot spots and detonation. The exhaust passages had to wind through the block in complex paths that could restrict flow and cause overheating. Farcus had to carefully balance combustion efficiency against manufacturing simplicity, finding solutions that would work in both the laboratory and the factory. The engine's displacement was set at 221 cubic inches, achieved through a 3.0625-inch bore and 3.75-inch stroke. The relatively small displacement was a deliberate choice. Larger engines would have been more powerful, but also more expensive to manufacture and more likely to encounter cooling problems. The compression ratio stayed conservative, around the mid-5-to-1 range, so it could run on the low-octane gas of the Depression years. Ford's commitment to the project was demonstrated by the massive investment in new production facilities. The Rouge River plant was expanded with new foundries specifically designed for V8 casting. New boring machines could hit surprisingly tight tolerances for the time, keeping all 8 cylinders consistent enough for smooth, durable operation. New assembly lines were designed to handle the more complex V8 while maintaining Ford's legendary production efficiency. The foundry operations were particularly critical to success. The casting process required precise control of iron chemistry, pouring temperatures, and cooling rates. Specialized cooling chambers maintained exact temperature profiles while protecting the castings from vibration that could create flaws. Quality control was built into every step of the process. Each casting was pressure tested for leaks, inspected for internal flaws, and dimensionally checked before machining. By early 1932, the first production Flathead V8s were running on Ford's test stands, producing 65 horsepower at 3,400 RPM and 130 pound-foot of torque at 2,200 RPM. At a price point only modestly above a four-cylinder Ford, it delivered roughly 60% more power, a remarkable achievement that seemed impossible just months earlier. The engine's public debut came at the 1932 New York Auto Show, where Ford displayed a cutaway Flathead V8 alongside complete Model 18 vehicles. Crowds gathered around the display, marveling at the engine's compact design and simple construction. Automotive journalists were initially skeptical. How could Ford produce a V8 so cheaply when other manufacturers charged premium prices for similar engines? The answer lay in Farcus's revolutionary manufacturing approach and Ford's willingness to invest heavily in specialized production equipment. By 1933, Ford was producing hundreds of thousands of Flathead V8s annually, making it the first truly affordable, mass-produced V8 engine in automotive history. But the Flathead's real impact extended far beyond passenger cars. Ford's commercial vehicle division quickly recognized the engine's potential for trucks and work vehicles. The 1932 Model BB truck became one of the first mass-produced commercial vehicles to offer V8 power at a price working people could afford. Though V8 was optional in 1932, most commercial buyers stuck with proven four cylinders until reliability proved out over the first few years. The transformation was immediate and dramatic. Contractors who had struggled with underpowered four-cylinder trucks suddenly found themselves able to haul heavier loads up steeper grades without overheating or stalling. The Flathead's strong, low RPM torque was perfectly suited to commercial work, meaning drivers could pull heavy loads from a standstill without lugging the engine. Construction companies embraced the new capability enthusiastically. Major contractors on big projects, including major dam and infrastructure jobs in the 1930s, used V8-powered trucks to haul materials into rough country, where older four-cylinder rigs struggled. The V8s could maintain reasonable speeds while pulling heavy trailers up steep mountain grades, something nearly impossible with four-cylinder engines. Large delivery firms found that V8 Fords could haul heavier loads and keep better schedules on hilly routes, enough to cut the number of trucks and trips they needed. The improved performance allowed them to consolidate routes and reduce fleet sizes while maintaining service levels across challenging terrain. The engine's distinctive sound became as important as its performance. The Flathead's exhaust note was unlike anything Americans had heard before, a deep, rhythmic rumble that announced the presence of 8 cylinders. The sound came from the engine's unique firing order and Siamese exhaust ports that routed through the water jackets, giving the distinctive rumble but also heat challenges. Agricultural applications proved equally important. Farmers had long relied on stationary engines for powering equipment, but Flathead-powered trucks could serve double duty as both transportation and portable power sources. During harvest season, these trucks could haul grain to elevators, then return to power threshing equipment using belt-driven power takeoffs. Police departments, including Detroit's, liked that V8 Fords could finally keep up with fast getaway cars, and they quickly became a staple of pursuit duty. Many fire departments adopted Flathead-powered pumpers, where low-end torque and simple mechanics were more important than cutting-edge horsepower. The extra power of V8 trucks helped push trucking beyond strictly local routes, especially before diesel power took over the heavy end of the market. Independent truckers, previously limited to short-haul work, began establishing longer routes. Well-maintained flatheads were known to rack up very high mileage for the era, making long-distance hauling workable for independent operators. This expansion of trucking capability helped lay part of the foundation for the modern freight transportation system. Small operators could now compete on routes that had previously required much larger, more expensive equipment. The democratization of reliable long-haul power opened new possibilities for independent businesses across America. During World War II, vast numbers of Ford military vehicles used Flathead-type V8s, running in desert heat, Arctic cold, and tropical humidity. The engine's simple design and robust construction proved ideal for military service, where field repairs had to be possible with basic tools and minimal specialized knowledge. Military applications pushed the Flathead to its limits and beyond. In North Africa, Ford trucks operated in extreme temperatures, often running continuously for days without shutdown. In the Aleutian Islands, the same engines started reliably in sub-zero conditions. Marinized versions powered various small boats, where their simplicity and torque were just as useful on water as on land. The post-war boom years saw the Flathead reach peak popularity. Returning veterans, familiar with the engine's reliability from military service, chose Ford trucks for their civilian businesses. The combination of proven durability and affordable parts made the Flathead the engine of choice for small contractors, farmers, and independent operators across America. Hot rod enthusiasts discovered the engine's potential for modification, leading to a thriving aftermarket industry. By 1950, there was a booming speed parts industry, with scores of companies producing performance parts for flatheads. Companies like Edelbrock and Offenhauser produced high-performance intake manifolds, carburetors, and cylinder heads specifically for the flathead, creating a self-sustaining market that kept flatheads competitive long after more advanced engines appeared. Racing applications showcased its potential when properly modified. At Bonneville and on drag strips, heavily modified flatheads pushed well into triple-digit speeds and proved they could make serious power in the right hands. Drag racing pioneers built their early careers on highly modified Flathead V8s that became the foundation of American hot rodding culture. But the engine's true legacy remained in commercial applications, where its combination of power, reliability, and serviceability made it the backbone of American industry. Small-town mechanics who understood flatheads inside and out could repair them with basic tools and readily available parts, making them ideal for rural and remote applications where sophisticated service wasn't available. Eugene Farkas continued refining the flathead throughout the 30s and 40s, introducing improvements like better cooling systems, stronger connecting rods, and increased displacement. Through the late 30s and 40s, Ford steadily enlarged the flathead, from the original 221 cubic inches to 239 and then larger variants, making around 100 horsepower in post-war form. These larger versions built on the same basic casting approach, refined over years of production. The fundamental simplicity that made the original design successful was maintained even as power output increased. Each evolution preserved the characteristics that made the flathead ideal for commercial and industrial applications. By the early 1950s, more advanced overhead valve V8s began challenging the flathead's dominance. Engines like Chevrolet's small block V8 offered better breathing and higher power output, gradually pushing the side valve design toward obsolescence. Ford introduced their own overhead valve Y-block V8 in 1954, marking the beginning of the end for the flathead era. The transition wasn't immediate or complete. Many commercial operators continued using flathead-powered vehicles well into the 60s, valuing the engine's simplicity and the extensive parts network that had developed around it. By the mid-50s, Flathead V8 production at Ford had ended after millions of engines had been built worldwide. Eugene Farkas retired from Ford in the early 1950s, his contributions largely unrecognized outside the company despite their revolutionary impact on American transportation. While Henry Ford supplied the vision and a whole engineering staff carried the load, Farkas's work on casting and design made the mass-market V8 possible. His innovations in manufacturing and design philosophy established principles that influenced engine development for decades. Eugene Farkas had taken V8 power from the exclusive realm of luxury cars and handed it to the masses, unleashing a revolution that changed the sound and strength of American machines forever.